Hello. We are going to go over parametric equations today. And in this video here, I'm going to kind of give you sort of a little bit of background or kind of a starter motivation, right, of why parametric equations are used and how are they sort of created. In your assignment, you're not going to go nearly as in depth as I'm going to go to in this video, and your notes don't go quite as in depth as the equations are going to be in here. But I think this is a good spot, like, okay, if you've I've never heard of this stuff, parametric equations before. I'd have no idea what any of that would ever mean. This is just a good jumping on point. However, I understand that like you guys have your own time. You don't have to watch this whole video. I'm not going to test you on the information that I'm going to go over here. But I do think it's important, and I do think it is kind of neat to see, like, okay, where do these parametric equations come from, and how would we even go about using them? Because like I kind of said, in your assignment, you're not going to need to do this, because the stuff I'm going to ask you to do in your assignment or on a quiz or a test or anything is going to be a much more simplified version than what I'm going to go over here. But I think it is nice to see where do these things get used and why do they get used a little bit. Okay, so in here, to start with this, I'm going to just sort of start out by showing you, here we've got this green point. It might be a little tough to see there because it's not really doing too much, but it's just this green point here. And what we're going to do is see, well, what does it do, right? Let's get this thing moving. So I've just got this thing here that, as time goes on, A is kind of representing, as it moves, what do we have, right? And so if I hit play on here, the point will start moving around the screen, kind of in almost a random order, although you can see it's kind of following a pattern, although it might be tough to discern what that pattern is just by watching it a little bit here, right? And we can slow it down a little bit more if we want to see that pattern. But if this thing was moving much faster, we'd start to really lose control of, kind of where it's going at all. So the thing is we want to be able to map where this point is going, right? What is it doing in here, right? How can we create an equation that would at all map the path of this thing, which would be very difficult if I tried to just make an equation that was like something x, something y, maybe equals a number, because it's definitely not following a circle or a hyperbola or a parabola or any of those shapes. It's clearly kind of bouncing all over here. So that equation would be very, very complex and very, very complicated. And it would definitely not be a function because it would not pass the vertical line test. So to make it a little bit easier, what we do is we make it into a parametric, or we pare down the equation, okay? And what we do is, instead of looking at where this thing is at in space, is we sort of map part of its position. We only look at part of its position, not everything at once. So for example here, maybe I'm only going to look at the vertical position. I'm just going to map it vertically, and I'm going to try to ignore the movement up and down, which is a little tough to do, just by covering up our eyes or trying to imagine that. So what I'm literally going to do is just turn that stuff off and look at just the horizontal part going up and down. And now it looks a lot easier, right? It's not moving all over the place. It's just going up and it's just going down. That's it, which we know what that is, right? Stuff that goes up and down and up and down and up and down. That's a sine graph, or perhaps a cosine graph, right? And so here, to determine if it's a sine graph or a cosine graph, I'm going to pause its movement for a second, back it all the way up to 0, and see, oh, at time 0, it's at maximum displacement. It's at its farthest it can be. So that means I would know that this thing has to follow a cosine graph, right? It has to follow that. And let's make it so that it matches in color as well, right? And I see too, it's at an amplitude or a height of 5. And as I hit play, it goes down to -5. So that means I know that the amplitude here has to be 5, right? And then what we would try and do is see if we, if we move this cosine graph, if we can get it to keep up with this coordinate, right? That's what we would want to do. So in here, right, what I might do is just put a +a, and that gets the graph kind of moving, right? We can see, oh, this graph is now moving, but it's not matching up to this point. You know, it's dragging a little bit, so we'll slow it down a little bit so it's a little, oh, maybe that'll make it a little smoother motion. So in here, but the point's moving a little bit faster than this graph is moving backwards to match it. So we've got to speed this graph up a little bit. And you guys know that that's the period. You know, we talk about spinning in a circle. That's kind of like this moving up and down. So we want this thing to go a little bit faster. So I might, you know, maybe double the rate of speed. So now we've got double the period. It's got twice as many waves going on in it here. And in this case, actually, I'm going to try something here and see if this just, yeah, there we go. We're just going to double its pace, but that's not quite fast enough yet. So maybe we could crank this up, you know, maybe go 4 times as fast. And it's still not quite fast enough. You know, this point's still moving a little bit more. And since I'm the one that made the equation, I know that it should be moving 8 times faster through here. Okay, once it's moving 8 times faster, this catches up to it. So we've got sort of an equation that, you know, moves through this point at the speed. We know it's horizontal speed. And remember, or sorry, we know it's vertical speed. And remember where this is coming from is it's just tracking the horizontal stuff of this point. Now I get it's not matching it, you know, or sorry, no, keep confusing my words here because I'm looking at them on the side. It's just mapping the vertical position. Notice this green dot is not matching up with this purple equation, which that was not at all my goal. The goal was just to match the vertical spot. You know, can I match its height? And that's sort of where we're getting to that parametric stuff. Again, this is more advanced than the stuff that you guys are going to do. And I don't know this off the top of my head. I simply know what this equation is because I created it ahead of time, right? This would usually take a little bit of work. You know, when we're looking at some stuff in motion, can we map how something is moving, right? So that's where we'd start, right? That would take some observation and some science and stuff. We would try and see that. So what I'm going to do now is say, well, we've got the vertical stuff down, or at least I have an equation for it, but I'm going to turn that off right now. And then what we want to do with this kind of point that's moving around, we've mapped its vertical components. Now we want to parse it into its horizontal stuff, right? I'm going to keep track of it and just track it horizontally. And then what we'll do is we'll sort of turn all of that stuff off and just track its horizontal movement. And as you can see here, you know, because I set it up this way, but it's still moving from 5 to -5 here. So that's probably a sine graph or a cosine graph, right? It's just moving between the two. So it's either a sine or cosine graph. And to tell whether it's sine or cosine, here I'm going to back this up to 0 and see, oh, it has 0 displacement at time 0, which means it's probably a sine graph, right? And in here, to get it to, since we're tracking, you know, horizontal movement rather than vertical, I'm just going to flip around my x and my y. Yeah, oops, let's go here. So I'm just going to, you know, make the sine graph go vertical rather than, you know, our other horizontal direction that we're used to. And that's because we're tracking this. And then we can see, yep, this is going to map over here and here. And then all I need to do is make sure that I try to get the speed right. So as we're moving this graph through, you see the point is moving faster than the graph is. So again, we could try and double this, and it's still not quite moving fast enough. The point's moving a little bit faster than our graph. And so we would just kind of say, okay, at 3 times speed, now it's moving at exactly the right pace. So what we have here is we have an equation, right, that is mapping its horizontal spot, that is matching this exactly horizontally. We also have an equation that is, you know, tracking this thing vertically as well, right? And I can put this equation on, but this starts to get a little bit crazy now, right? There's a lot of stuff going on. All this stuff is moving at once still. It's like this is more complicated than it was before, right? Than what we had initially to begin with. But what we can do here is, you know, sort of put these two equations together. Since this is x value and this is our y value in essence, we can sort of just track where's this point at, at a particular point in time. So what I mean by that, what I'm going to do instead here is I'm just going to pull this open. And what I have is I just have this thing mapped out a little bit. And notice here, I have to change it a little bit, but the x value is 5 times sine, and then 3, the equation is 3 times some value, right? That's what's happening in here. So that's what I put in for the x value in this case, 5 times 3 times t in this case, t representing time. Right? That's why I had to use a out here, because in Desmos, t represents time, because Desmos can do these parametric equations. You can see that's where that green point is. And then I can map the y values here. The y-axis is 5 cosine 8 speed, so I put that in x comma y. And then this is just to make it into a point. I put the a value in there. But we can see that this thing, sure enough, maps that equation right there. We can see the vertical mapping. I mean, we can have all these equations on here, but we don't necessarily need them. This is the particular path that that point is following, right? And to get this equation into just like x equals y stuff, that would be very, very difficult to do. This is, not an easy equation to graph unless we're going to do that in what's called parametric form like we're doing here. And just to show you a little bit more about kind of what that is doing here, let me turn off all this horizontal and vertical stuff here. I'm going to pause this for a second, back it all the way up. And what's really happening, okay, time is in essence starting at time 0, right? And then it's mapping it to a particular thing. So until a particular point. So I'm just going to make the time go to a, right? So that it matches whatever this number is. So what happens here, I'm going to slow it down just a little bit, is as we start moving at time 0, it's right here. The graph is not there. But what we can do is sort of track where is it at as we increase the time. Where is it going? Okay? And that's just because it's just mapping part of that equation. But this is essentially what a lot of kind of physicists do. This is jobs like at NASA where they're tracking, an orbital body as it's going through space. They're putting things in parametric equations, although their parametric equations are much larger, and they're also tracking things in 3 dimensions, not just 2-dimensional space like we're doing here. So their equations get much more complicated very, very quickly. But this here can give us a little bit of like, okay, that's what we're doing. When things are in motion, sometimes it's a little bit easier to see that. And yeah, the computer's having a little bit of trouble keeping up with it because you can see it kind of pulsating there in the background. But that is what a parametric equation is. It's just another way to graph more complicated things. And then this will end its way back up. It'll kind of circle back around and back at where it started again. That's why I have it as 2 pi, because it's kind of completing a full cycle of this whole graph. So that's what, in essence, a parametric equation is, which, hopefully gives you a little bit of, how these parametric equations kind of work. We're tracking, the horizontal and vertical motion of some point that is moving through space. And so that gives you at least a little bit of a background and maybe a little bit of a motivation, or a higher level motivation. And then what we're going to do, and that's what I'll explain in the next video on those notes, is just kind of the very basics of just scratching the surface of these parametric equations.